Hello everyone, welcome to this video. In this video, we are going to talk about magnetism and material. In the previous lectures, we talked about what is magnetism, how a moving charge is giving rise to magnetic field. Then we also discussed about how a current carrying wire is getting affected by the magnetic field. So what happens when you have two or three current carrying wires? What happens to the magnetic field and all? We studied about all this. Now we are going to look at magnetism in the material perspective. Like what are the different materials with respect to the magnetic field and what happens to the magnetic field when we put different materials in it. So these are the things we are going to discuss in this lecture. So the earth itself behaves as a very big magnet with the magnetic field pointing approximately from the geographic south to the north. When a bar magnet is freely suspended, it points in the north-south direction. This we already know that when you suspend a bar magnet in a thread, if you freely suspend it, it always points towards north to south. And this principle is used in magnetic compass when you're traveling in ocean, and if you don't know the direction, then you can use a compass to find what is the north. So this is because the earth itself acts like a magnet. So the tip which points to the geographic north is called the north pole, and the tip which points to the geographic south is called the south pole of the magnet. There is a repulsive force when north pole or south pole of two magnets are brought close together. Conversely, there is an attractive force between the north pole of one magnet and the south pole of the other. So this we already know that north pole and south pole of two magnets get attracted, and the north pole of one magnet repulses the north pole of other magnet. We cannot isolate the north or south pole of a magnet. This is a very important property of a magnet because you cannot isolate north and south pole. Even if you take a bar magnet and cut it into 1,000 pieces, you cannot separate a north pole from its south pole because the magnetic monopole do not exist. So the magnetic monopole doesn't exist. Electric monopoles exist. So electric charges can be positive or negative, they can be separated. But when it comes to magnetism, you cannot separate a north pole from a south pole. So if a bar magnet is broken into two halves, we get two similar bar magnets with somewhat weaker properties. Unlike electric charges, isolated magnetic north and isolated magnetic south poles, known as magnetic monopoles, do not exist. Okay, now let's look at a bar magnet. So when you take a bar magnet like this, when you take a bar magnet and let's say you keep paper on top of it and sprinkle some iron fillings in it, then the iron fillings will look like this. This looks like there are two poles, one here and one here, and the magnetic field lines are represented by this iron filling. So this is the uh, exactly what happens when you have a bar magnet and put iron fillings on it. So this pattern of iron fillings suggests that the magnet has two poles similar to the positive and negative charge of an electric dipole. So this looks like an electric dipole, right? If you have a positive charge here and a negative charge here, and how the electric field lines go from one charge to other charge, this is similar to that. So if this is a bar magnet, we can assume one pole is a north pole and the other is a south pole. So one pole is designated north pole and the other is the south pole. When suspended freely, these poles point approximately towards the geographic north and south poles respectively. A similar pattern of iron fillings is observed around a current carrying solenoid. So now this is an important point. When you have a current carrying solenoid, we already saw what happens to a current carrying solenoid and how a magnetic field is produced in that. And that is similar to a bar magnet. So the pattern of iron fillings permits us to plot the magnetic field lines. So if you want to plot the magnetic field lines, just use some iron fillings and they will trace the magnetic field lines like this. Okay, now we will look at the magnetic field lines of a bar magnet. The magnetic field lines of a magnet or a solenoid form continuous closed loops. So this is an important point, and this is a point which is different than the electric dipole. So this is unlike the electric dipole where these field lines begin from a positive charge and end on the negative charge or escape to infinity if you have a single charge. But in the case of magnetic field lines, they do not start from one point and end at another point. They always form continuous closed loops. Like the one shown here, you see these are the continuous closed loops. The loops close inside the material, but if you have an electric dipole, the field lines start from one point and end at another point. Now, the tangent to the field line at a given point represents the direction of the net magnetic field B at that point. So this is similar to the electric field. So if you have a field line here, if at this particular point you draw a tangent, and that tangent will tell you what is the direction of the magnetic field at that particular point. The larger the number of field lines crossing per unit area, the stronger is the magnitude of the magnetic field B. So this is again similar to electric field case when we count the strength of the electric field based on the density of the field line. So this is similar to that. So in figure B, based on this principle, we can say that region 2 has more number of magnetic field lines. So the field is stronger here compared to this area where the field is weaker. So the magnetic field lines do not intersect, for if they did, the direction of the magnetic field would not be unique at a point of intersection. So this is also similar to electric field lines. They do not cross each other. The magnetic field lines never crosses each other, because if they crossed each other at that point, then the magnetic field will have two different directions. So that is not possible. Even if they had two different magnetic fields, then the resultant will be in only one direction. So the magnetic field lines do not cross each other. Okay. Next one is the bar magnet as an equivalent solenoid. So we already talked about this, how a bar magnet and a solenoid produces similar magnetic fields. Now we are going to derive how a bar magnet acts as a equivalent solenoid. So the magnetic dipole moment M associated with the current loop is defined as M equal to N I into A. So where N is the number of turns in the loop, so this is for the case of a solenoid. If you have N number of turns and I is the current, A is the area. We already studied this. So magnetic moment is given by current multiplied by area of the loop. If you have N number of loops, then it is N multiplied by current multiplied by the area of the loop. Now the magnetic field lines of a bar magnet and a solenoid are similar, so that a bar magnet may be thought of as a large number of circulating currents in analog with a solenoid. It can be shown that the axial field of a solenoid at a larger distance resembles that of a bar magnet. So you have a solenoid and you see the axial field, that means the field at the axis of the solenoid. If you go to greater distances, that means R is much greater than L, then you get the field as similar to a bar magnet. So what are they implying is, when you have a bar magnet and when you have a solenoid, the field looks exactly same at a distance. So the solenoid in the figure consists of n turns per unit length. Now its length is L and radius is A. The axial field is to be evaluated at a point P. So the axial field means the field at the axis of the solenoid. Now at a distance R from the center O of the solenoid, at a distance Z from its center. So this is the set A and this is the distance R from the solenoid, from the center. Now it has n dx turns. So if you take a small element here dx, it will have n dx turns because n is the number of turns per unit length. So if you multiply with the length dx, then you get the number of turns in this n dx length. I is the current in the solenoid. Now if you want to find the magnetic field at a point P due to the circular element, we already derived this in the last lecture. So dB equal to mu 0 n dx Ia square divided by 2 into r minus x the whole square plus a square the whole power 3 by 2. Now x is the distance of this particular element from the center. And now if you take that, note that the range of x is from minus L to L, because that is the length of the solenoid. So it x ranges from minus L to L. Now consider the far axial field of the solenoid. That means this A is the radius of the solenoid. But if R becomes much larger than A and also much larger than L, so it is much larger compared to the length of the solenoid and also the diameter or the radius of the solenoid. In that case, what happens? This factor in the denominator becomes r cube, because x is also, a is also very less, L is also very less compared to r. So we can approximate this as r cube. And then b becomes, if you approximate this as r cube, mu 0 ni a square divided by 2 r cube. Now dx varies from minus L to L, so we will integrate dx from minus L to L to get the overall field. So what happens here? So finally we will get 2L. So mu 0 ni by 2, 2L a square divided by r cube. So this is the magnetic field at a point P in the axial direction of the solenoid at a distance r from the center. So this is the value. Now note that the magnitude of the magnetic moment of the solenoid M will be NIA. We know that it is NIA, and now N is the total number of turns. So N multiplied by 2L is the length of the solenoid. So this gives us total N, capital N, multiplied by the current through the solenoid and the area of the loop. So pi a square, a being the radius of this circle. So now if you replace this N, I, 2L and a square and pi by this M, then you get B equal to mu 0 by 4 pi, because there is a pi here, multiplied by 2m divided by r cube. So this is nothing but the magnetic field of a bar magnet. So this is also the far axial magnetic field of the bar magnet. Thus a bar magnet and a solenoid produce similar magnetic field. So that is our conclusion. So what we did is, we took a solenoid and derived the magnetic field at the center or the axial point of the solenoid. Then we got the expression which is similar or same as the magnetic field from the bar magnet. Now the magnetic moment of a bar magnet is thus equal to the magnetic moment of an equivalent solenoid that produces the same magnetic field. So from this we can conclude that the bar magnet also acts as a solenoid and its magnetic moment is given by this M. Okay, so now we will see what happens to a dipole in a uniform magnetic field. We discussed a same thing in the electric field case, where we took an electric dipole and kept it in the electric field, and then we found out that it rotates. Why it rotates? Because there is equal and opposite forces acting on positive and negative charges. So there is a torque. Similarly, here also the same thing happens. So if you keep a magnetic dipole is nothing but a compass which has a north and south pole. So you take a small compass needle of known magnetic moment and it is kept in a magnetic field of magnitude B, and it is allowed to oscillate in the magnetic field. That means it is allowed to move freely in the magnetic field. So what is the torque that is produced here? It is M multiplied by B. It is similar to the torque produced in electric field, where it is P multiplied by E. So here it is M cross B, and cross product, so we can say MB sine theta, theta being the angle between B and the dipole, magnetic dipole. So here tau is the restoring torque and theta the angle between M and B. So when we say restoring torque, it is similar to spring force. When, for example, if you extend a spring, the spring comes back to its original position. So there is a force that restores the original position. So that is the restoring force. For example, if you rotate this dipole, rotate this magnetic moment or a compass, it tries to come back to its equilibrium position. So that is what we call as restoring torque. Now I is this moment of inertia. So we can write this equation as tau equals to I multiplied by d squared t by dt squared, which is equal to minus mb sine theta. So this is similar to our simple harmonic motion equation. We will see that. So now this negative sign implies that the restoring torque is always in opposite to the deflecting torque. For small values of theta, it can be approximated that sine theta equal to theta. So we will say, substitute sine theta equal to theta here. So I d square theta by dt square equal to minus mb theta. And let's take this I to this side. So then we will get d squared theta by dt square equal to minus mbi into theta. So this is similar to d squared x by dt square equal to minus k by m into x, which is nothing but the simple harmonic motion equation. So if we relate to that and then find out what is omega square from the previous equation, then we get omega square equal to mb by I being the moment of inertia here, and the time period will be, from omega we can get the time period, which is t equal to 2 pi into square root of I by mb. So now from this time period we can rearrange this and then find out what is the magnetic field. So magnetic field is 4 pi squared I by mt square. So an expression for magnetic potential energy can also be obtained on lines similar to electrostatic potential energy. We already calculated U for electrostatic potential energy when a dipole is kept in an electric field. So similarly, when a compass is kept in a magnetic field, the potential energy UM is given by integral of tau of theta into d theta, and so we get minus mb cos theta, otherwise minus m dot b. This is a dot product. So now we have the liberty to assume the reference as 0. So we can take reference as 0 when this thing becomes 0, when theta cos theta becomes 0 is 90 degree. So we can take that as a reference. So taking the constant of integration to be 0 means fixing the 0 of potential energy at theta equal to 90 degree, and when the needle is perpendicular to the field, that is when the potential energy becomes 0. Okay. So now let's discuss what is Gauss's law, and in with respect to magnetism, what happens to Gauss's law. So the net flux is 0 when the number of field lines entering a closed surface is equal to the number of field lines leaving the surface. So whenever you take a closed surface, when we calculate the net flux, what do we say? It is equivalent to the number of field lines coming out or the number of field lines going in, net number of field lines, right? So if there is equal number of field lines entering the closed surface and also equal number of field lines leaving it, then the net flux is going to be 0. So this is from Gauss's law. So in the case of electric field, if the closed surface contains any charges, the next net flux will not be 0. So for example, in this case, this is a electric dipole, this is plus, this is minus. So we have a region here 2, we have a region here 1. If you look at 1, the number of field lines entering is equal to the number of field lines coming out of it. So the net flux in 1 equal to 0. But if you look at net flux in 2, the number of field lines coming out is much more than number of field lines going in, because there is no field lines going in, all the field lines are coming out because there is only one positive charge inside. So in this case, the net flux is not 0. So this is from Gauss's law. But if you look at this diagram here, the region 1 and region 2, in both the cases the flux is 0, because this is for a magnetic field, and magnetic field lines always form closed surfaces, so they do not come out from any charge or any pole. Even if you look at this region 2, see, the number of field lines, magnetic field lines entering here are coming out here. So the number of field lines coming in is equal to the number of field lines going out. So the net flux is going to be 0. This is very different compared to the electric field line case, because in electric field lines the flux need not be always 0, but in the case of magnetic field the flux is always 0. So the magnetic flux will be 0 for any closed surface. Isolated magnetic monopoles are not known to exist. So phi b is nothing but the magnetic flux. If you take all the surfaces and add all the magnetic fluxes, then b dot delta s is going to be 0. But in the case of electric field, the E dot delta S is not 0 because it has Q by epsilon 0. In this case, it cannot be Q by epsilon 0 in the magnetic case because magnetic monopoles do not exist. So the net magnetic flux through any closed surface is 0. So this is the conclusion we are arriving from this discussion, that the in the case of magnetic field, the net flux has to be 0 for any closed surface. Okay, now let's just have a look at what is Earth's magnetism. So in the introduction, we discussed about Earth acts like a big magnet. So now let's just look into it more. So the magnetic field lines of the Earth resemble that of a hypothetical magnetic dipole located at the center of the field. So if you look at the magnetic field lines that are coming out of the Earth, it can be equivalent to what happens when you keep a very big magnetic dipole inside the core of the Earth. So the magnetic field lines resemble that. So the axis of the dipole, but the axis of the dipole does not coincide with the axis of rotation of the Earth, but is presently tilted by about 11.3 degree with respect to the later. So this is the axis of rotation of the Earth, and this is geographic line, North Pole and the South Pole. But the magnetic North Pole and the South Pole is making an angle 11.3 degree with this line. So there is a small deviation in the angle. It doesn't coincide with the geographic north and south pole. So the location of the north magnetic pole is at a latitude of 79.74 degree north and a longitude of 71.8 degree west, a place somewhere in North Canada. So that is where the North Pole is located. The magnetic South Pole is located in Antarctica at these angles 79.74 degrees south and 108.22 degree east. So this is the location of magnetic North Pole and the South Pole. These magnetic poles are located where the magnetic field lines due to the dipole enter or leave the earth. So the pole near the geographic north pole of the earth is called the north magnetic pole. Likewise, the pole near the geographic south pole is called the south magnetic pole. Okay. Now we will look at what is magnetic intensity. So now we have come to the discussion what happens when you keep a material in a magnetic field. So we already talked about this in the last lecture, that if you have a electron revolving around a nucleus in an atom, it gives rise to a magnetic moment, right? So we will look into it more. A circulating electron in an atom has a magnetic moment. In a bulk material, these moments add up vectorically and they can give a net magnetic moment which is non-zero, because a bulk material is nothing but a collection of atoms, molecules, right? So if you have one atom and there are some electrons revolving around the nucleus, it's going to give rise to a magnetic field, magnetic moment. And if you have a collection of atoms like this, there's going to be a lot of magnetic moments created and they are going to add up vectorically depending on the direction of the magnetic moment. Again, the direction of the magnetic moment depends on the direction of revolution of the electron. Is it counterclockwise or clockwise? It depends on that. So based on that, all the magnetic moments are going to add up and it will not be necessarily zero all the time. So what is magnetization? We are defining something called magnetization, which is the magnetic moment per unit volume. So for example, if you have 1 gram of a material, you take a square shaped material and you take what is the total magnetic moment. That means all the atoms are contributing to the magnetic moment. Find the total magnetic moment and divide it by the volume. So this is nothing but magnetic moment per unit volume, and this is nothing but the magnetization of that particular material. So consider a long solenoid of n turns per unit length and carrying a current I. The magnetic field in the interior of the solenoid was shown to be given by P0 equal to mu 0 Ni. So we are using a 0 here because this is a solenoid and inside the solenoid there is nothing but vacuum or air. So in this case, B0 equal to mu 0 Ni. This is the magnetic field in the core of the solenoid, in the interior of the solenoid, produced because of the current passing through the turns. Now, if you take the solenoid and fill it with some material with non-zero magnetization, now what happens to the magnetic field in the interior of the solenoid? It will not just be B0 in this case, and there will be Bm. Bm is something that is coming from the material and M stands for the magnetization. So, where Bm is the field contributed by the material core. So in this case, what we are doing is we are taking a solenoid and keeping a material inside. Now the field inside the solenoid is not just B0 and has another component called Bm. And this Bm is the contribution that is coming from the material core. So remember that this Bm can change based on what material you are keeping inside. It turns out that this additional field Bm is proportional to the magnetization of the material and is expressed as. So this field, as I said, this field Bm is coming from the material and it depends on the magnetic moment per unit volume of the material, because it makes sense. Whatever magnetic moment is given by the material, that much magnetic field only it can produce. So Bm equal to mu 0 into M. So now let's see what happens to the total B. So now we are going to define another quantity called H, which is magnetic intensity, which is defined as H equal to B by mu 0 minus M. Now B is the total field and M is the magnetization of the material. So this is again coming from this equation. So we can define H as B divided by mu 0 minus M. If you rearrange this equation, you get B equal to mu 0 H plus M. So this is the overall field inside the solenoid. There are parts that contribute to the magnetic field inside the material. So if you look at the magnetic field inside the material, one due to the external sources like the current in the solenoid, that is denoted by H. So this H is coming because of the current in the solenoid. So you can control it. You can even call it as an external magnetic field. And now the other part is due to the specific nature of the magnetic material called M. So this depends on how the material responds to the magnetic field. So now this M equals to chi multiplied by H. So this M equal to chi H is, it's also very important how M is directly proportional to H, because H is now the external magnetic field. You're keeping a material inside an external magnetic field. So the magnetization in the material has to be obviously dependent on the external magnetic field. So that's why M is directly proportional to H, and that proportionality constant is chi. So now this chi is the magnetic susceptibility. It's a measure of how a magnetic material responds to an external field. So it's straightforward from this equation. M is directly proportional to H, and how M behaves for H depends on the chi. So this is what decides what will be the behavior of M. So that's what this statement says. It's a measure of how a magnetic material responds to an external field. So this value is small and positive for magnetic materials which are called paramagnetic. It is small and negative for materials which are diamagnetic. In the later case, M and H are opposite in the direction. So there are some materials called diamagnetic where the magnetization is opposite to the applied field. So we will see what is paramagnetic and diamagnetic. Okay, so we will just expand this equation a little bit. We have B equal to mu 0 H plus M, and let's substitute M equal to chi into H here. So then you take H outside, then you get B equal to mu 0 1 plus chi into H, and this 1 plus chi we can define as mu R. So this mu R is nothing but 1 plus H, 1 plus chi is a dimensionless quantity called the relative magnetic permeability of the substance. It's the analog of the dielectric constant in electrostatics, where if you remember, we have epsilon in the case of electrostatics, the dielectric constant. It is similar to that. This is magnetic permeability of the substance, which is mu. So mu equals to mu 0 and mu r. We know that mu r is 1 plus chi. So the product mu 0 and mu r we can define as mu, which is nothing but the magnetic permeability of a particular substance. The three quantities chi, mu and mu r are interrelated. If one of them is given, the other two can be easily determined. Okay, so based on these quantities chi and mu r, we can classify the materials as diamagnetic, paramagnetic or ferromagnetic. In terms of the susceptibility chi, a material is diamagnetic if chi is negative, paramagnetic if chi is positive and small, and ferromagnetic if chi is large and positive. See, for a diamagnetic material, it's less than 0 and negative 1 if it falls on this range. For a paramagnetic, it is greater than 0 but it is smaller than the epsilon. For chi very much greater than 1, it's a ferromagnetic material. So now see, we have studied how a material responds to the magnetic field, and now we have classified the materials based on its response as diamagnetic, paramagnetic and ferromagnetic. So we will study this one by one. So let's see what is diamagnetic. So we already discussed in a diamagnetic material, chi is negative. When chi is negative, M equals to minus of H or minus some constant into H. So what does it mean? The magnetization in the material opposes the applied field, right? So that is the basic for diamagnetism. So diamagnetic substances are those which have a tendency to move from stronger to the weaker part of the external magnetic field. That means they get repulsed by the magnetic field. They don't move towards the magnet. If you have a diamagnetic substance, it's not going to move towards the magnet, but it's going to move away from the magnet. So the figure shows a bar of diamagnetic material placed in an external magnetic field. The field lines are repelled or expelled and the field inside the material is reduced. See, if you keep a diamagnetic material like this in a magnetic field, the field lines don't go through the material. They just avoid the material and they go around it. So if you look at the field inside, they will be less than the applied field, because now obviously M is negative. When M is negative, obviously B total is going to be less than the B applied. So electrons in an atom orbiting around nucleus possesses orbital angular momentum. These orbiting electrons are equivalent to current carrying loops and thus possess orbital magnetic moment. So now we are explaining the origin of diamagnetism, why it happens. We know that electrons in an atom orbiting around the nucleus give rise to an orbital angular momentum, and this gives rise to a current loop, and this gives rise to an orbital magnetic moment. So in diamagnetic substances, the resultant magnetic moment in an atom is zero. So when you apply a magnetic field, this electrons having orbital magnetic moment in the same direction slow down and those in the opposite direction speed up. So what happens when the electrons having magnetic moment in the opposite direction speeds up means the magnetic moment in the opposite direction will increase. That means the magnetism will be opposite to the applied field. So this happens due to induced current. Thus, the substance develops a net magnetic moment in direction opposite to that of the applied field, and hence there is a repulsion. So examples of diamagnetic materials are bismuth, copper, lead, silicon, nitrogen, water, and sodium chloride. And diamagnetism is present in all the substances. The most exotic diamagnetic material are superconductors. So you might have heard about superconductors. What are superconductors? These materials are normal conductors in normal temperature. When you reduce the temperature, they suddenly become superconductors. Their resistivity becomes almost zero. So these are metals cooled to very low temperature, which exhibit both perfect conductivity and perfect diamagnetism. So here the field lines are completely expelled. So chi equal to -1 and mu of r equals to 0. So these are a very good example for diamagnetic materials. Okay, now let's talk about paramagnetism. So we know what is paramagnetism from the table. For paramagnetic material, chi is positive and small. So positive means what? M is in the direction of H. So now the magnetization of the material is along the direction of the applied field. So the fields can go through the material, go inside the material. So, paramagnetic substances are those which get weakly magnetized when placed in an external magnetic field. They have the tendency to move from a region of weak magnetic field to strong magnetic field. They get weakly attracted to a magnet. The individual atoms of a paramagnetic material possesses a permanent magnetic dipole moment of their own. On account of the ceaseless random thermal motion of the atoms, no net magnetization is seen. See, for example, when you have a paramagnetic material at the higher temperature, they will have permanent dipole moments, but they will be randomly oriented, so they cancel out each other, so the net magnetization is zero. But when you reduce the temperature, what happens? They get more magnetized and the magnetization increases. So the magnetic moment of a paramagnetic substance or magnetization of a paramagnetic substance depends on temperature, and this dependency is given by Curie's law. So let's see what Curie's law says. In the presence of an external field B0 which is strong enough and at low temperatures, the individual atomic dipole moment can be made to align and point in the same direction as B0. So the susceptibility depends on temperature in this way, C multiplied by mu 0 by T. And C and mu 0 are constant, T is the temperature. So this is how it depends on temperature. So it is inversely proportional. So when temperature reduces, chi increases. So the magnetization also increases when the temperature reduces. Okay, now let's look at ferromagnetism. So unlike the paramagnetic materials, the ferromagnetic substances are those which get strongly magnetized when placed in an external magnetic field. They have strong tendency to move from a region of weak magnetic field to strong magnetic field. They get strongly attracted to a magnet. So the materials which get strongly attracted to a magnet generally are ferromagnetic materials. Now, what is the origin of this ferromagnetism? The individual atoms or ions or molecules in a ferromagnetic material possesses a dipole moment as in a paramagnetic material. However, they interact with one another in such a way that they spontaneously align themselves in a common direction over a macroscopic volume called domain. So these are the domains. See, if you look at the magnetic moments inside the domain, they are arranged in a particular order, unlike the paramagnetic materials, because in paramagnetic materials it is completely random and the net magnetization is zero. But in a ferromagnetic material, the origin of magnetic moment is same, but it is not zero because the domains are interacting with each other and they are aligned in a particular direction, in a random direction. So when you apply a magnetic field, all the domains align in the same direction and you get a very high magnetic field. Sorry, magnetization. Overall magnetization is high when you apply a magnetic field. When we apply an external magnetic field B0, the domains orient themselves in the direction of B0 and simultaneously the domain oriented in the direction of B0 grow in size. So that overall it becomes aligned in the direction of the magnetic field. So we get a very high magnetization. So the ferromagnetic property also depends on temperature. At high enough temperature, a ferromagnet becomes a paramagnet because the domain structure disintegrates with the temperature. So when you have a very high temperature, the thermal energy overcomes the applied magnetic field's energy. That means the magnetic moments become random at higher temperature. So it becomes a paramagnet like the one we studied previously. But at low enough temperatures, the magnetic field can align the domains in the same direction, so they become magnetized. Again, so it is also temperature dependent, but the dependency is little bit different compared to the paramagnetic case. So the temperature of transition from paramagnetic to ferromagnetic to paramagnetic is called the Curie temperature Tc. So this is like a phase transition, like from liquid phase to solid phase, how phase changes. It is also a phase transition from paramagnetic to ferromagnetic. So the susceptibility above the Curie temperature can be given as chi equal to C by T by Tc when T is greater than Tc. So when T is greater than Tc, the material is like a paramagnet. But when the temperature becomes less than Tc, less than the phase transition temperature, it becomes a ferromagnet. So let's say an important property of a ferromagnet and how it behaves with applied magnetic field. So the relation between B and H in ferromagnetic material is complex. It is not so simple like a paramagnet. Like a paramagnet, we saw how M equal to chi into H, that's all. But here it's little bit different. It is often not linear and it depends on the magnetic history of the sample. So when we say magnetic history, what we mean is whether the material is previously magnetized or not, whether the material is already exposed to a magnetic field or not, it also affects the behavior of this curve. So the curve means B versus H curve. So in x-axis we have H and in y-axis we have the B, the total magnetic field. So figure depicts the behavior of the material as we take it through one cycle of magnetization. Let the material be unmagnetized initially. So the material is at a point O. Now we are we are putting the material inside a solenoid so that it can experience a H, and the magnetic field B in the material rises and saturates as depicted at the curve OA. So we are increasing the current in the solenoid. So we are increasing H. When we increase H, it traces this path and it goes to saturation at A. So it goes through O to A. Now this is the saturation is happening because all the domains are now aligned perfectly with the magnetic field. There are no more domains to align. So now it has reached a saturation. Now what happens when you reduce the field again and you bring it to 0, that means H equals to 0, B is not equal to 0. So when you again make H equal to 0, but B is not equal to 0, so it traces a path A to B. So the curve A to B is represented when H equal to 0 and B not equal to 0. The value of B at H equal to 0 is called the retentivity or remnants. The domains are not completely randomized even though the external driving field has been removed. Now look at it carefully. Now you're applying from 0, you're applying a field and you're saturating, so all the domains are completely aligned. But again you're reducing the field, external field, and bringing it to 0. But even then, some of the domains are not completely random. They are still giving rise to a magnetization. This is because the domains interact with each other, just like how we talked about in the beginning. So the domains interact with each other and they form some sort of an alignment. That's why when H equal to 0, B is not equal to 0. But in paramagnetism, when H equal to 0, B has to be equal to 0, right? Then next the current in the solenoid is reversed. So now let's reverse the current in the solenoid and let's apply minus H. And at this point the B becomes 0. So this is the curve BC. So certain domains are flipped until the net field inside the strands are nullified. This is represented by the curve BC. As the current is increased further, saturation is achieved. This is represented by this curve CD. Saturation is up in the negative side. And look at it now, the curve OA is not traced in the negative side. So because it is already magnetized in the positive side, now it goes through CD only. It does not follow OA again. So for a given value of H, B is not unique but depends on the previous history of the sample. This phenomenon is called hysteresis. This loop is called hysteresis loop, and this is a characteristic of a ferromagnetic material. Okay. Now let's look at permanent magnets and electromagnets. So what are permanent magnets? Permanent magnets are the materials which have the ferromagnetic property even at room temperature for a long period of time. These are called permanent magnets. So the permanent magnets can be made in many ways. An efficient way to make a permanent magnet is to place a ferromagnetic rod in a solenoid and pass a current. The magnetic field of the solenoid magnetizes the rod and it becomes a permanent magnet. So the hysteresis curves allow us to select suitable materials for permanent magnets. The material should have high retentivity. Why it should have high retentivity? Because when you remove the applied magnetic field also, the magnetization of the material has to be strong. So that's why it has to have high retentivity and high coercivity. The material should have high permeability also. So steel has a slightly smaller retentivity than soft iron, but this is outweighed by the much smaller coercivity of the soft iron. So other suitable materials for permanent magnets are alnico, cobalt and ticonol. These are the alloys which can be made to act as a permanent magnets. Okay. So what are electromagnets? So core of the electromagnets are made of ferromagnetic materials which have high permeability and low retentivity. Soft iron is a suitable material for electromagnets. So on placing a soft iron rod in a solenoid and passing a current, the magnetism of the solenoid is increased by 1,000-fold. So you keep a solenoid and generally what will be the magnetic field inside the solenoid, and if you put a ferromagnetic material inside the solenoid, the magnetic field now is increased by 1,000-fold. So this magnetic field we can use for many applications, and this is called an electromagnet. And one beautiful thing here is you can control the magnetic field by controlling the current through the solenoid. So this is a flexibility because for many experiments you need to tune the magnetic field to a particular value. So in some applications, the material goes through an AC cycle of magnetization for a long period. AC means the source here will be alternate current, like in the case of transformer cores or telephone diaphragms. In transformers, we know that we have two cores and we have solenoids, and inside the cores there are some materials and it acts as an electromagnet. So their AC field is playing a role. So electromagnets are used in many cases like electric bells, loudspeakers and telephone diaphragms. Thank you.